Chapter 12, Video 2. We are going to be continuing on with our chi-square distribution discussion. In this video, we are going to be looking at a test of homogeneity. Now, previously, we had talked about a chi-square goodness of fit test in Video 1. And with a chi-square goodness of fit, we were looking at one categorical variable against one population. So what's going to make a chi-square test of homogeneity different? Well, if the distribution of one categorical variable still, but it's different across either two or more populations or two or more treatments in an experiment. So the only big difference between the homogeneity and the goodness of fit is we're looking at one population for a goodness of fit versus multiple populations with a test of homogeneity. And again, notice I said two or more. Oftentimes we will look at two, but we could look at three different populations, four different populations. This is commonly used in medical studies where they're looking at various treatments being different or not different with respect to different populations. So the problem we're going to take a look at says movie attendance dropped dramatically during the COVID-19 pandemic, but was attendance already on the decline before that due to an increase in at-home on-demand video access? Separate random samples of 1,002 adults from 2001 and 1,025 adults from 2019 were asked how often they went to the movies. Do these data provide convincing evidence the distribution of movie theater visits changed from 2001 to 2019? We're going to use an alpha level of 5%. Now, one of the big differences you'll notice here with a test of homogeneity versus a goodness of fit test is previously with a goodness of fit test, we really had like just one column of data. We had a list. And now we're going to have more of a two-way table. So we will need to change strategies for how we are going to input our data into our calculator. And you might be familiar with the approach that we're going to use. Maybe if you have taken pre-calc or maybe even algebra 2, the way that we are going to input our data might be familiar to you. If not, just really slow down the video, pause and slowly go. Now, when we take a look at our data, we can see in 2001 that we had either, very few visits to none, 0 to 1. Maybe they moderately went to the movies 2 to 5, or maybe they went to the movies a lot. They went 6+ times in a year. And in 2001, it was almost fairly even, right? We got 331, 320, 351. And then in 2019, we can see the people who went a lot, that number decreased. The number that went a moderate amount of time went up compared to 2001. But so did the number that maybe went once or none at all went also up from 2001 to 2019. So in our test of homogeneity, what is our one categorical variable we're exploring? Well, that would be our movie theater visits. And what are our two or more populations? We're going to be comparing two different years, people in 2001 and people in 2019. Now, how do we get those expected counts? Because when we had a goodness of fit test, we had two different situations. Either we were given probabilities to consider that we would need to look at our sample size, and we multiplied those given probabilities to us, like the M&M proportions, by our sample size to get our expected counts. Or the other type of chi-square goodness of fit test that we looked at was if things were evenly distributed, and then we would just take our sample size and we would split it up into however many categories we had. And that's how we would determine the expected counts. But it's going to be a little different with a test of homogeneity. The way that we're going to calculate the expected counts is to take the row total times the column total divided by the total total. Now, by the total, I mean the true grand total of, in this case, our combined populations from 2001 and 2019. Now, let's go ahead and start filling in this expected counts table here. So if I wanted to figure out the 0 to 1 for 2001, well, the row total would be this 710, and I'd multiply that by the column total, which would be everybody from 2001, and I would divide that by the grand total of everybody, 2027. Now, most of the time you're going to get some decimal numbers. So I would recommend just rounding these to 1 or 2 decimal places is absolutely fine. Now, when I do that math, I get 351.0 rounded to the nearest tenth. Now, if I were to do the next one, and you might think, oh my gosh, we got to do this 6 times? Not really, not really. Here's what's going to happen here. Here, let me get rid of that. Let's take a look at, let's say the 2 to 5 for 2001. The only thing that's going to change is that 710 is going to go to a 689. The column total is still the 1002, and our total is still 2027. So we can make a slight adjustment in our calculator, and then we could get that this expected count is 340.6. Now, from here, this is what it makes me kind of feel like I'm doing a Sudoku puzzle in a way. It's not quite a Sudoku puzzle, but from this point, I can figure out what all of these other numbers are without necessarily doing the row total times column total divided by total, because these 3 expected counts all have to add up to be 1002. So what I could do in my calculator is take 1002, subtract 351.0, subtract 340.6, and what am I left with? 310.4. Now, the same thing's going to apply with our rows, that 351 plus this number needs to make a total of 710. So if I start with the 710 and subtract 351, I get 359. If I then take 689 and subtract 340.6, I get 348.4. And then last but not least, if I take 628 and subtract 310.4, I get 317.6. So there are all of my expected counts. And what's kind of cool is the way that we had to kind of keep using the expected count formula, right? We had to end up using it twice to then be able to figure out what all the rest of the numbers were. And that really is going to tie into our degrees of freedom that we're going to have for two-way tables. So more on that to come. Now, what do the hypotheses in general look like for a test of homogeneity? So we're looking at the distribution of whatever our one categorical variable is not different among our populations or our treatment groups. It depends on what the problem is set up to be here. Versus alternatively, the distribution of that one categorical variable is different among the populations or among the treatment groups. So what does this look like exactly for our movie attendance problem? Well, the null hypothesis would be that the distribution of our one categorical variable was the movie theater visits is not different from our populations 2001 to 2019. Versus alternatively, we would say the distribution of movie theater visits is different from 2001 and 2019. Now, I had heard a teacher explain for the null hypothesis, if you ever get confused about, well, geez, is it supposed to be different or not different? The null hypothesis, I've heard, is called the dull hypothesis, D-U-L-L. It's just kind of the plain, the vanilla, the ordinary. And so the plain, ordinary, vanilla of a null hypothesis for a test of homogeneity is just to say things are not different. I mean, that's just not exciting if they're not different. But what we want to show is that the distribution of our one categorical variable is different among our different populations or our different treatment groups. All right, conditions. These are going to look really, really familiar. Number one, the random condition. It must state that the samples are random, SRSs, or that they use random assignment. Now, here's the thing. Remember, we had 2 separate random samples. Let me jump back here for a second to here. Separate random samples of 1,002 and 1,025 adults from those 2 separate populations. So in a test of homogeneity, if we're looking at different populations, you have to have separate random samples from those separate populations. So don't just say, a random sample was taken. We need multiple random samples were taken. Or again, if this was some sort of experiment, then maybe they just say all the treatments were randomly assigned to the volunteers. And then basically saying it used random assignment implies that went amongst all the different volunteers to cover all of our different populations of interest. Number 2, the independent condition. Now, if random assignment is used, then we don't necessarily need to check the independent condition. But there were random samples in this problem. And so what we need to do is use the independent check for each of our populations. And there were two separate populations. We had all the adults in 2001 and all the adults in 2019. And we can safely say that there were, 10,020 and 10,250 adults in both of those years. I'm assuming we're looking at this nationwide. Now, the large counts condition, this is the same exact one as it was for our goodness of fit. We need all of our expected counts to be at least 5. And we already figured out that the smallest expected count was 310.4, so easily met. Now, calculations are basically going to be the same exact thing like it was for a chi-square goodness of fit test. It's going to be the same general chi-square statistic formula where we take each observed count minus its expected count, square that difference, and then divide it by the expected count. Now, you can see here that I didn't write out all 6 possibilities using that formula. I did the very first one. So I did the top left corner, and that's where I started this off with. And then I pretended like I went all the way through this table, and then I ended with the bottom right corner here. So this can be your abbreviated work, showing that you understand that it's not just one observed minus expected squared divided by expected, but it's that you have to add up all of the different possibilities here. So in the end, there are technically 6 of these individual values, and in the end, we're going to add them all together. Now, I listed out what all the individual chi-square test statistic values were, just so we could see them and kind of look at them and see like maybe where the most off value was. But in the end, our chi-square test statistic is a total of 15.22 approximately. Now, we take that chi-square test statistic. We need to convert it into a p-value. We're still going to end up using chi-square CDF, just like we did with the goodness of fit problem. And remember, chi-square test statistics are always positive. So we are always going to look at a greater than or equal to situation, which means our test statistic will always be the lower bound, and infinity will always be the upper bound. Now, for degrees of freedom, this is going to be different than the goodness of fit problem. The degrees of freedom for a test of homogeneity and also for our third and final test, chi-square test in video 3, will just be the number of rows minus 1 times the number of columns minus 1. So we have to remember we're only supposed to be looking at the actual counts here, not looking at the subtotals, because that's where sometimes people will get into trouble. They'll think back and they'll go, oh, there were 4 rows of data and there were 3 columns of data, when in fact there was only 3 rows and 2 columns. So in the end, 3 rows and 2 columns is going to give us a grand total of 2 times 1, which is 2 degrees of freedom. Now, if you remember earlier, whenever we were calculating the expected counts, and I mentioned something about how the degrees of freedom were really tying into the number of times that we had to use that expected count formula, that the row total times column total divided by total went into play. And once we found out these first 2 expected count cells, then from there, we didn't really need to use that formula anymore. So once we had used that formula twice, and that does tie in directly with our degrees of freedom. Because consider, this is the number of rows minus 1, there's 2, times the number of columns minus 1, well, that's just 1, and 2 times 1 makes 2. All right, so let me reveal the p-value here. So once I use my chi-square CDF command, and again, this is in the same place as normal CDF and tCDF. If you press second variables to get to distribution, you're just going to have to scroll down even further to find chi-square CDF. We get a very small p-value. And again, you can write it in scientific notation, or you can write it out as 0.0004955. Now, how do we do this with our calculator? And I mentioned earlier, there's a different approach to this. We're not going to use lists. We are going to use matrices. And for some of you, you might be familiar with matrix math in your calculators, and some of you may really have no idea where matrices are even located, and you might not even have a whole lot of experience dealing with matrices. But that is not a big worry. A matrix is essentially like a multi-dimensional list. Instead of it just being like one column, we can have multiple columns. And that combination of all those lists of data is essentially our matrix. So if you want to get to a matrix, you have to press the second button and then go down to the what I would call the inverse button, this x to the -1. And you'll see right above there it says matrix. Now we're going to want to scroll over to the edit part, and we're just going to go ahead and put this into matrix A. Now, there might be a chance that you could actually see some numbers right here that maybe once upon a time you've actually done some matrix work. And it's okay, we're just going to write over this matrix. So even if you have numbers here, just go ahead and select matrix A. Now, it's going to initially ask you, how many rows and how many columns? What size do you need this matrix to be? And by default, it always says 1 by 1, unless you already have a matrix in there. Then it might have other numbers. So I'm going to type in a 3 and then press enter and then press 2 and then press enter, and then it will create me a 3 by 2 matrix. The first number, again, is always the number of rows. The second number is always the number of columns. So then I can go in and put in, and these are going to be my observed counts, the ones that I was initially given here. So every time you put in a number, you press enter, and then it takes you over. It takes you always over to the right, and it's just basically going to zigzag through the matrix here. So you start with this top left, then it goes to the top right, then it goes down to the next row, and then over to the next column, and then down to the next row, and then over to the next column, until you have the whole thing filled out. Now, the one thing I failed to mention is you do need to name this procedure if you're going to use the calculator with the matrices. And so we have to name this as a chi-square test of homogeneity. There is no abbreviating this one. Like with a goodness of fit, we call that a GOF test. You can't call this a TOH. I honestly have never seen anybody try to abbreviate it, but I would just let you know you're going to have to name this thing out. Some people are then going to ask, what if I misspell homogeneity? Not a problem. As long as you are close enough, you'll get the credit. Now, once we have our observed counts into a matrix, into matrix A, we are going to go to press the stat button, and then we're going to go over to tests where we've been the last, 4 chapters at this point. And in video 1, we used this chi-square GOF test. But for video 2 and video 3, we are going to select the one that just says chi-square test. So select option C, and by default, observed will say matrix A. And that's why I always recommend let's put our observed data into matrix A. Now notice it says expected is matrix B, and we didn't put our expected counts into matrix B. But here's what's nice. The calculator will automatically calculate the expected counts for us and put it into matrix B for us. So we don't even have to really mess with the expected counts. Now you might be going, well, then why did we calculate them earlier? Well, if you were going to do this problem by hand with the formula, then you would need to know what the expected counts are to be able to use this test statistic formula. We also needed to know what the expected counts were for the large counts condition, right? We needed to know how big was the smallest expected count, and we already figured out that it was 310.4. Now, I do have a recommendation later on once we go through the full calculator command. We'll kind of loop back around, and we'll talk about some strategies we could do here. So I just got to say, matrix A is my observed count. We're just going to leave expected as B. We're just going to leave that alone. Go hit calculate, and the 3 things that it tells us, we are going to need to write down on our paper. Here's the chi-square test statistic. You can go 1 or 2 decimal places. Here's our p-value, which is slightly different than the one we had come up with the chi-square CDF command. And it's all just because of little rounding differences. Roughly, it's the same thing. Notice degrees of freedom. It automatically did the degrees of freedom for us. Remember when we did a chi-squared goodness of fit test, we had to tell the calculator how many degrees of freedom there were. But as a matrix, the calculator can look at the matrix and see how many rows and columns there are, and it'll automatically do that math for us to tell us that there are 2 degrees of freedom. Now, it would be a really good multiple choice question if I gave you a test of homogeneity problem and I said, how many degrees of freedom would there be in this problem? And it's going to be really easy for you just to go, oh, well, that's just rows minus 1 times columns minus 1. And in this problem, that would be 2. Versus if you went and did all of this in your calculator just to see that there were 2 degrees of freedom, you just wasted a lot of time. But it is a strategy. Now, if we go back to our matrices, if we go back second to that x-1 button, that inverse button, and now if we go over to edit, we'll notice that matrix B says it is now a 3x2 matrix. And so if I press enter on matrix B, then it's going to show me all of those expected counts. So like I have here, did we really need to calculate them all earlier? Not really. But again, we needed to know what the smallest count was for that large counts condition. So if you're not going to do the chi-square test statistic by hand using that formula, and you really just need to know what is the smallest expected count, just so you can verify that condition, what you could do is just write out the condition and then basically, I don't know, put a star, circle it so that you know you're not fully done with it. And then when you go actually get to practically to the end of the problem, and then you go look at the expected counts, then you can look through your expected count matrix and go, ooh, look, there's the smallest expected count. Now let me go back to the third condition and say the smallest expected count was 310.44. And then you can just proceed on from there. The other thing that you could do instead of doing that is whenever we were first looking at, let me jump back to when we were doing the expected counts. When we were at this point right here, so let me clear this off. The easiest way to find the smallest expected count is to look at your 3 subtotals, in this case, and your 2 subtotals, in this case, for your columns, and just identify the smallest numbers in each of those subtotals. So 628 is our smallest subtotal for the rows, and 1002 is the smallest subtotal for the columns. So if at all, I was just to use this formula one time, if I did 628 times 1002 divided by 2027, then I could figure out truly what the smallest expected count is. So if that's the only one that you do, then so be it. Then you'll know what the third condition is really supposed to be. When you say the smallest expected count is this number, and that's greater than or equal to 5, and you can move on from there. All right, so let's get back to here. Now, another big difference between a goodness of fit test and a test of homogeneity is in our goodness of fit test, we have that little list at the bottom, that CNTRB for those contributions, and it told us all the different possibilities that added up to be our total chi-square test statistic. So where are those numbers when we do just a regular old chi-squared test in our calculator? And they're just unfortunately nowhere to be seen. So if you wanted to figure out which value was the most off, you would technically need to do the observed minus expected squared divided by expected for each and every possibility to see which one was the most off. Now, in this scenario, I can see this is the largest value out of all 6 possibilities. This would really be the bottom left, which would be that smallest expected counts one. So this would be the group that was in 2001 that went to the movies a lot, 6 or plus times. So this one was the most off compared to all the other possibilities from 2001 and 2019. So in the end, our final conclusion, regardless if you use the calculator command or the chi-square CDF command to get the p-value, you can see these are relatively close to each other. And in either situation, they are way smaller than 5%, so therefore we reject the null hypothesis. And in the end, we can state that we do have enough evidence, sufficient evidence, convincing evidence at the alpha equals 0.05 level to conclude that the distribution of movie theater visits is in fact different from 2001 to 2019. So before COVID was even a thing, we can statistically conclude that movie theater visits were changing from 2001 to 2019. Now, what I would like you to do is I've given you a new set of data to consider, and this is looking at two countries, the United Kingdom, good old England, and the United States. And they took a random sample of people from both countries, and they asked them, what superpower would you prefer to have? Flying, freezing time, invisibility, super strength, or telepathy? And so here's the data on the left side. What I want you to do is to figure out what are all the expected counts in this table over here on the right, what is the overall chi-square test statistic, what is the p-value, and what are the degrees of freedom for this problem. Now, in this scenario, I didn't say you had to do this by hand, so if you want to use the calculator and use a matrix and practice with using a matrix, you could certainly do that for this particular problem. And we'll talk about this the next day in class. Good luck.